Hi, welcome to Red Hat Ceph Storage Performance video series. I'm Daniel Parks and I will walk you through episode 4, where we will share the results of our tests regarding Red Hat Ceph Storage Performance Scalability. We will explain the performance increase we get when scaling out the OSD node count of our Ceph clusters. Traditional storage systems normally have a scale-up architecture built around two controllers that are connected to several disk shelves. When the controller reaches 100% utilization, this creates a performance bottleneck, so it doesn't matter how many disk shelves you add, that you will only increase the capacity of the system. The performance will remain the same or even gradually get worse. With software-defined storage solutions like Red Hat Ceph Storage, you don't have to face these kind of problems. When nodes are added, performance and capacity always increase together. The flexible scale-out features of Ceph eliminate many of the challenges associated with today's massive data growth, allowing linear improvement in performance and capacity. For these tests, the methodology that we followed was to first run the benchmarking with 3 nodes and then repeat the same tests after scaling out the OSD node count to 5. So during the scale out, we are adding new hardware resources. We are adding more NVMe devices, more CPU cores, and also RAM. In this slide, we compare the IOPS and average latency before and after scaling out the Red Hat Ceph storage cluster. Looking at the graph, we have on the vertical axis IOPS represented by columns. The blue column has the IOPS of our 3-node cluster before scaling out. The red columns have the IOPS of the cluster after scaling out to 5 nodes. The horizontal lines represent the average and tail latencies, again blue for 3 nodes and red for 5 nodes. The x-axis has the 3 workloads or patterns that we tested. Random read, the mixed workload with 70% read and 30% write, and random write. If you remember from the previous episode where we took a look at the 4K results with 5 nodes, we saw that the OSD nodes had a very high CPU utilization, limiting the performance of the cluster. As you can imagine, when we ran the 4K test with the same number of clients, 105, against a smaller cluster with 3 nodes, the CPU saturation was even greater, with the CPU run queue on the Ceph nodes skyrocketing during the duration of the test. So adding what we can see from the results of these tests is that adding 60% of additional hardware resources, we were able to deliver up to 90% higher IOPS, around 46% lower average latency, and 44% lower tail latency. So we can confirm that adding nodes to an existing cluster not only improves the capacity, but also we get better performance. And like in this case where the actual cluster is saturated, when we scale out, we also reduce the average and tail latency for the client workloads. In this slide, we have the results of a client sweep test, where we gradually increased the number of clients. We used a random read pattern with a block size of 4 kilobytes and an I/O depth of 64. Like in the previous graph, blue represents 3 nodes and red represents 5 nodes. In the x-axis, we increment the number of clients up to 140. We can see that the blue columns representing the 3-node configuration barely increase the number of IOPS during the duration of the test. That's because with an I/O depth of 64, even with 30-40 clients, the CPU utilization in our 3-node cluster is very, very high. With 5 nodes, we are better prepared to sustain the pressure as we increase the client load. That's why we not only have a higher number of IOPS with 5 nodes, but also we have lower latencies. To check how the performance keeps improving, it would have been very interesting to be able to scale out again, so we could run the test with 3, 5, and then 7 nodes. But we didn't have more hardware available, so that kind of test wasn't possible. In this slide, we have large block scale-out performance. When talking about large block sizes, we are normally interested in the maximum throughput the cluster is able to produce. In this graph, we are testing with a block size of 1 megabyte. Again, we have the 3-node configuration in the blue columns and the 5-node configuration on the red columns. We have on the x-axis the 3 patterns that we use during the test. So random read, our mixed workload, where we have 70% read and 30% write, and also our random write test. In episode 2, we mentioned that our total bandwidth from the client uplink to the Ceph servers was limited to 80 gigabits per second. With 5 nodes random read tests, we have the same problem. We are bottlenecked by the client network throughput, which is why we are seeing performance peak at around 10 gigabytes per second. If we had more bandwidth available between the clients and the Ceph clusters, we could assume that the throughput gain with 5 nodes compared to 3 nodes would have been bigger. With the other 2 patterns, we have in the mixed workload an improvement of 15% in throughput, and with the random write, we have an improvement in throughput of 67%. So the overall performance improvement after adding 2 additional nodes was not significant compared to what we have seen in the small block workload. A quick summary of episode 4. For small block sizes, after scaling out from 3 to 5 nodes, we were able to get 95% higher IOPS and considerable lower latencies. With large blocks, 1 megabyte in this case, testing random read, we were limited by the client throughput, so there was not a big difference between 3 and 5 nodes. With the random write pattern, the throughput improved by 67% after scaling out the cluster. So the key takeaway is that with Red Hat Ceph Storage, when you are scaling out, you not only increase the free space available, but you also improve the performance. That's all we had for episode 4. Thank you for your time. I hope you enjoyed it, and please keep tuned for the next episodes. Thanks, bye.